All right, this is Jasper. Oh, and there's a bunch of them coming now. There's a horde of, yeah, that was Willa. There's a horde of cats coming now. We're trying to crush out a couple more videos. In this video, what we're going to do is we're going to take these two vectors, and they want a lot of information, but they want a magic vector, which is a unit vector perpendicular to these two original vectors, and then also forming an acute angle with the positive x semi-axis. So there's a lot of information to decompose. We'll decompose them one at a time, and then we'll re-put them together and answer and find this final vector that they're looking for. Okay, you can get down. Good? Yeah. The first thing that they're doing is the unit vector is relatively easy, but what that is has length 1. So I think we're going to call it W probably. So what we want from W is the unit vector means it has to have length 1. Perpendicular to both of those guys immediately shows to me that it's going to be U cross V is the vector perpendicular to U, and U cross V is perpendicular to V. That immediately tells me also that we have a check in these types of problems. That should be Pavlovian at this stage. That says U cross V dot product U has to be 0, and U cross V dot product with V has to also equal 0. So when we create this vector using the cofactor expansion, using Cramer's rule, or not Cramer's rule, using cofactor expansion along the top row in this 3×3 determinant, when we compute this, we have an efficient form. Once we get that vector, we can check to see whether we did it right by checking the dot product with the original 2. Once we've done all that, we'll have a vector, but it wants an extra condition. It wants to have an acute angle with the x semi-axis. So we'll find a vector in the direction of that, and then we'll take the dot product, and we want that to be positive in this case. So let's start doing this. The first thing we need is the cross product of U cross V is equal to the 3×3 determinant of I, J, K. Then I put U in the second row, 4, -2, 2, and I put V in the third row. Then I cofactor expand along the top row. This is knowing what the formula is. I times the 2×2 determinant obtained by blocking off row 1, column 1, so this. So I'm going to get -2, 2, 0, -1. Minus, because of the checkerboard pattern, or because of the cofactors, minus, oh, we're going to have to sneak it in, J will block off row 1 and column 1, so 4, 2, 1, -1, and then plus K times the last 2×2 determinant, which is blocking off this and this, which is this 2×2 determinant, which will be 4, -2, 1, 0. So this is now equal to 2 times I. And then I'm going to get -4 minus 2 is -6 times another negative is +6J. Don't skip steps if you want to do those. Those are 2×2 determinants, and that's what I'm computing. I just didn't write it down. In this one, I get 4 times 0 is 0, minus 2 is 2. Okay. And remember, everybody always forgets, but I is the vector 1, 0, 0, and J is the vector 0, 1, 0, and K is the vector 0, 0, 1. So I'll do it once because this is the whole point of the videos. I is 1, 0, 0, plus 6 times J is 0, 1, 0, plus 2 times 0, 0, 1. Then I'm going to do scalar multiplication of these, and then I'm going to do addition and get the vector, which is the cross product. So moving that up magically, we get U cross V was this guy who I turned I into 1, 0, 0, J into 0, 1, 0, and then K into 0, 0, 1. Once I do that, now I do scalar multiplication. That becomes 2 goes into every spot, so that'll be 2 and then 0, 0, plus 6 goes into every spot, but that will be 0 times 6 times 0. And then plus 2 goes into every spot, and that will give me 0, 0, 2. Then geometrically adding these vectors at the front or the back or all at once, you can see we're going to get essentially this 2 plus 0 plus 0, 0 plus 6 plus 0, 0 plus 0 plus 2. So we in fact get the vector 2, 6, 2. And that's how at the end of cross product, how they're magically turning this guy into this. And everybody says, how did you turn that into a vector? It's because I, J, K are three-dimensional vectors already. The moral of the story here is first step one is compute U cross V. We have that. U cross V is now 2, 6, 2. As a quick aside, let's check. U cross V dot product with U should be equal to 2, 6, 2 dot product with 4, negative 2, 2, which is 2, which is equal to 2 times 4 plus 6 times negative 2 plus 2 times 2, which is equal to 8 minus 12 plus 4, which is equal to 12 minus 12, which is 0. So it seems like the dot product, this is the correct vector because it should be orthogonal to both, and I just checked that the dot product is. As an exercise, you can do this for yourself. If you put 1, 0, minus 1 in there, you'll also get 0. 2 minus 2 is 0. This is the correct guy on an exam. That gives you a check anytime they make you compute a cross product. However you're computing it or memorizing it, it better have dot product 0 with the two guys that they gave you originally, which it did. Now what do they want? Now they want, let's call this W is U cross V, which is 2, 6, 2. To find our final vector, we're going to call it A or B or something like this. It doesn't matter what you call it, but I want a unit vector. To create a unit vector, we can create A, which will be W over the norm of W. Any vector which I take the norm of that vector and divide it by that, I get a unit vector automatically. So how do you get a unit vector in the direction of any vector they make you create? I divide it by its length and I get a unit vector. So what is the length of this? We're going to get the norm of W is equal to the square root of 2 squared plus 6 squared plus 2 squared, which is the square root of 4 plus 36 plus 4, which is the square root of 44, which is the square root of 4 times the square root of 11, which is 2 root 11. You can slow that down, algebra. So once I have that, that says that our unit vector will be 1 over 2 root 11 times our original vector 2, 6, 2. And I can't help myself to simplify a little bit. I can see that I can cancel the 2 in each one, so I have a 2 in each spot. So what I see is A is equal to 1 over 2 root 11 times 2 times 1, 2 times 3, 2 times 1. So this is 2 over 2 root 11 times 1, 3, 1. Cancel the 2, and this is 1 over root 11 times 1, 3, 1. This is our vector, which is a unit vector. Unfortunately, we're still not done because some unnamed professor likes to make really complicated problems. Solomonovich, I'm talking about you. What I now want is this vector has to create a dot product which is positive, so I can create a acute angle with the positive semi x-axis. So what are we doing in that last part of the problem? Basically, I'm doing this. I now have this this unit vector, so I have most of it. I have A is 1 over root 11, 1, 3, 1. This has norm 1. It is in the direction of, and it's perpendicular to both U and V originally. And what I now want is, what Mark is talking about is, now I've called out both first and last name. If you can piece that together, you'll find out who I was talking about. So I have we're going to call this the y-axis. And this is in fact, so what he's talking, this would be the positive y semi-axis. This is the x-axis, and this is going to be the positive x semi-axis, and this is obviously the z. And then we would have, and then there's 4 octants, just like there, instead of 4 quadrants, we have 1, 2, 3, 4, 5, 6, 7, 8 octants in the 3 dimensions. So what he's asking now is, this vector has to form an acute angle with a vector in the direction of this one. We just discussed those a second ago when we're computing cross product. The vector in particular that we're looking for is the vector I, who is 1, 0, 0. So what he's saying in that last statement of the question is, can you find the vector, this one, which is dot product with this guy, is a positive number? If you look at that quickly, when we do the dot product, it has to do with the first coordinate. So when we look at that, I want A dot product I to be positive. Indeed, we have A dot product with I is equal to 1 over root 11, 1, 3, 1, dot product with 1, 0, 0, which is equal to 1 over root 11, 1 times 1 plus 3 times 0 plus 0. Those are zeros. So all we needed was this to be positive. So if you had computed and the cross product had negatives, you computed the other v cross u, or the other vector standing perpendicular to the other ones, and it would have had 3 negative coordinates, and you would know that would be the wrong one because it would create an obtuse angle. But because we got, when we computed this, our vector that we've already created, and the dot product with I is already positive, so that is the correct vector. The vector that does all the things that we want is indeed this vector. So it's like it's been so long now, I don't remember what they were. 4, negative 2, 2, and v is 1, 0, negative 1. Given these two original vectors, he wanted a vector which was orthogonal to these two vectors, has a length of 1 or is a unit vector, and forms an acute angle with this direction or with I, and A does all three of those things.